A software engineer successfully trained human brain cells grown on a silicon chip to play the video game Doom. Now, he has co-founded a Y Combinator summer 2026 startup to build the operating system and training algorithms for biological computing. Are biological wetware chips the future of energy-efficient intelligence? Meet Parasma, a biological compute company in the latest Y Combinator batch. Rather than building hardware, Parasma is creating the software layer and machine learning training protocols for human neurons grown on silicon. Their goal is to turn living biological tissues into reliable, highly energy-efficient computational units. This builds directly on the Organoid Intelligence breakthrough pioneered by Cortical Labs. In 2022, their DishBrain system successfully played a video game. Parasma's founder Sean Cole designed the Python code that translated game visuals into electrical stimulation and read neuronal firing responses to drive the gameplay. Why is biological compute so energy efficient? Traditional silicon chips rely on massive electrical currents pushed through copper gates, creating heat and requiring megawatts of power at scale. Living neurons, however, compute using chemical ion channels, sodium and potassium ions moving across cell membranes. A biological synapse fires using just 10 to the minus 15 joules. This means a wetware computer can process complex reinforcement learning tasks on a fraction of a single watt, matching the efficiency of the human brain, which runs on just 20 watts. Is this a true general intelligence? No, this is what scientists call organoid intelligence. While digital neural networks try to simulate thinking using static code, living brain cells have innate synaptic plasticity. They rewrite their own physical structure, growing new connections to adapt to stimuli and minimize environmental surprise. It is not artificial general intelligence, but biological general intelligence, capable of self-directed learning without being programmed. How do you train human brain cells to compute? Through biological reinforcement learning. The system stimulates the neurons with sensory data, reads their microvolt outputs as actions, and applies electrical feedback as a reward signal. Over time, the neurons adapt and establish learned synaptic pathways. What are the real-world applications of this technology? In the short term, Parasma's training algorithms enable high-throughput drug screening, allowing pharmaceutical companies to test how experimental compounds affect living human brain cells without animal trials. In the long term, this technology promises ultra-low power edge computing. Imagine drone navigation grids, robotic controllers, or deep space probes driven by biological cores that require zero cooling and almost no electrical power. Traditional silicon AI demands massive server farms consuming megawatts of power. Biological neural networks operate on less than a single watt, boasting self-routing connections and synaptic densities that silicon cannot match. It represents a completely different paradigm of computation. While commercial organic computing is in its infancy, Parasma is building the algorithms to program biology. It is one of the most audacious bets in Y Combinator history. Subscribe to Use AI with TechDad for more deep dives into system architecture and share your thoughts in the comments.